All right, this is lesson 10.4. It's the last lesson of unit 10. Today our topic is solids of revolution. So a solid of revolution is just a three-dimensional object that's formed by rotating a two-dimensional shape about an axis. So this first figure here shows a rectangle, and it shows that axis of rotation, which in this case is vertical, and we rotate that rectangle about that axis, and it sort of sweeps out the shape of a cylinder, which you can see in that last picture. So if you think about the original rectangle, this shorter side of the rectangle ends up being the radius of the cylinder, and the longer side of the rectangle in this case ends up being the height of the cylinder. And there's nothing, it's not going to always be that way. It won't always be that the short side is the radius and the long side is the height. That's just what it happens to be in this case. So we're going to look at some different shapes today that are solids of revolution, and we're going to be calculating their volumes. So we're going to start with a right triangle here. This right triangle is going to be rotated about the x-axis. So we're going to be rotating it in this direction. And we want to describe and name the solid of revolution that will be formed, and then we want to find the volume of that shape. So I just want to demonstrate this for you. Let me pull up some software. So here's that same rectangle, and I'm going to just tell my computer to rotate this shape. And so it's starting to rotate that top edge of the triangle down, and it's rotating it around. And if I move this around, you can see that the shape that we have created is a cone. See it one more time, maybe from another perspective. Oops, sorry. Here we go. So you can see it maybe looking at it sort of from the bottom of the cone. And there it goes again. Okay, so I like to draw a little arrow over on the side like that because that helps me sort of picture the way that the cone is laying. So this point right here is going to rotate down to the -2 spot over here. So that's going to be the base of our cone, and then here's that other side of the cone. So in this case, our triangle had a leg that had a length of 4 and a leg that had a length of 2. This leg right here, that's going to be the height of the cone, and then the other leg right here that has a length of 2 is going to be the radius of the cone. So we're going to find that volume. The volume formula for a cone is, and it's on your formula sheet if you need it, 1/3 of the circle times by the height. So we have 1/3 of pi times the radius squared. Well, the radius was 2, and we multiply that by a height of 4. It's important that you correctly identify which is the height and which is the radius. If you flip-flopped these, it would not be the same volume. So 1/3 pi, just calculating that, and it is about 16.8 cubic units. So same triangle, it has a leg of length 4 and the other leg is length 2, and this time we want to rotate it around the y-axis. Well, in this case, the shape that it creates, or the figure that it creates, is quite a bit different. So here's our same triangle that we're starting with, And this time I'm going to tell the computer to rotate it around the y-axis. And here it goes. So if we look at it from one perspective, we see a cylinder. If we look at the other side, it's somewhat like a bowl. So what this figure is this cylinder that has a cone sort of cut out from it. So I'm going to kind of do that rotation again from this perspective. Here it goes. So you can kind of see that that upper edge, the hypotenuse of the triangle, is sort of creating that bowl shape. It's a straight edge though, it's a cone that's been cut out, and the bottom leg of the triangle is creating this cylinder. And if we look at it, again, if we look at it from another perspective, all we see is the cylinder. But if we look at it from the top, we see that sort of cone that's missing. So we're going to calculate the volume of this shape, and we have to do it just how I've described, and that is that we have to think about it as this larger cylinder with a cone removed. So we're going to think about the volume of the cylinder, and we're going to think of the volume of the cone. Well, a cylinder formula is just pi times the radius squared, so there's our circle, times by a height. Cone is almost the same, it's just 1/3 of the circle times the height. Well, in the case of the cylinder, the radius is 4, and the height of that cylinder, I'll color that green, is right here. That height is 2. And we can calculate that. It's about, oops, sorry, I pushed the wrong button on my calculator. About 100.5 cubic units. For the cone, if we think about the radius of the cone, it's up here, I guess, if we're thinking about directly the base of the cone's kind of upside down, but it's that same radius of 4, and the height of the cone is the same as the height of the cylinder. It's 2. So it's 1/3 of pi times the radius squared times 2. So in this case, the volume of the cone is about 33.5. So if we want to know the volume of this figure, which is a cylinder with a cone removed, we just would subtract that. The volume of this shape would be 100.5 subtract 33.5, which gives us a volume of about 67 cubic units. So some of our shapes are going to be straightforward like this one, and some of them are going to be something that you have to think about in a compound way, either through adding two shapes together or subtracting. So here's an interesting shape. It's somewhat like a sine curve on the top of it there, and we're going to rotate that about the x-axis. So if we try to sketch that, our rotation is in this direction. So that's going to come down, and this top part here would rotate down out to here. And we would create something that you might imagine is maybe a flower vase. So in this case, we don't really have a way to directly calculate the volume here. We could estimate the volume maybe using a couple of cylinders. Maybe we sort of estimate it to be a wide cylinder here and a smaller cylinder through here, and then a bit wider one here. So we definitely could do that if we needed to find the volume. Calculus gives us a way to directly calculate that volume. But in this case, we're just going to think about cross sections of this flower vase. So the first cross section that we want to think about is the one formed by cutting it with the plane that sort of contains the coordinate axis. So in other words, we're cutting it maybe with my board here. So the cross section would look a lot like what we just have drawn already, just not so three-dimensional. And it would look something like this. And again, I'm not being super exact here, just getting it roughly correct. But it would be flat because it's cross section. If we thought about the cross section in the other direction though, for example, if we cut it right here at x equals 5, you can imagine that the cross section would be a circle. And if we wanted to be specific about the size of that circle, it has a radius of just about 5. 1, 2, 3, 4, 5. Maybe a little bit bigger than 5. So we've got a circular cross section with a radius of about 5. Wow, that's not my best circle ever, but it's okay. All right, well, what if we cut it at x equals 10? Our cross section is still going to be a circle, but this time our radius is closer to 3. So it's a little bit smaller cross section at x equals 10. And at x equals 15, we would be right at the end. So it would have a radius of 1, 2, 3, I think it's about 4. Should be close to 4. So something about that big. So different cross sections or different sizes of cross sections depending on where you cut that shape, but what they all have in common is that they would all be circles, just different sizes of circles. So for this shape, this bell, we want to draw the two-dimensional cross section that could be revolved around the x-axis to generate it. So we're just thinking about the basic shape and we're using our x-axis here. So this bell would maybe be created by a shape like this. I guess in this case I'm thinking about it having a solid bottom, so if you wanted to be more specific to a bell, it would maybe look something like this. And again, we're just looking for a rough idea. We're not going to measure or be too specific. Here's a nice vase. It has a narrow neck and maybe something like this. And then we have a rocket. Now the rocket presents a bit of a problem because it has fins. So we're going to have to disregard those fins and just draw the basic shape of the rocket. It starts at a point, it's a little bit wide and then flat. And if you were getting super fancy, you could draw some fire, but not really, just for fun. All right, so if we were thinking about this rectangle, if we wanted to rotate it about the x-axis, and again, you have to pay attention to what your axis of rotation is, this would create something like this cylinder, and maybe like a can of soup or something would be that shape at your house. One more final shape. We have this trapezoid and we want to rotate it about the y-axis. So we're rotating in this direction. And this is kind of a weird shape, so I want to show you what that shape is going to look like when we rotate it. Let me pull it up in the software. So here's our little trapezoid, and we're going to revolve it around the y-axis. So I just need to tell it to use the y-axis, and we're going to revolve that around. And there it goes. And let me show you from another perspective what we've just rotated that trapezoid to make. So let's see it from a different perspective. So starting with that original trapezoid, and there it goes. So if you have a hard time visualizing these things in 3 dimensions, you'll get better at it, and we'll practice. So here's a drawing on the board of that shape. It's called a frustum. That's one of the names for this shape, but also sometimes called a truncated cone. So we're going to calculate the volume of this shape, and we're going to do, and we're going to use that idea of a truncated cone to help us. So what a truncated cone means is that it's a cone, it's a slice of a cone. We can think of it as the bottom slice of a cone if we want. So I'm going to draw the cone that I'm talking about. Let's see, I'll do it in blue. So if I kind of think of extending that back and doing the same over here, you can see the cone. And what we're going to do is think about a second cone that is a little bit smaller. So we're going to find the volume of that larger blue cone, and we're going to subtract the volume of the smaller red cone. So for that larger blue cone, our volume is going to be 1/3 pi r squared, so 1/3 of the circle times by the height. So this is for the nice big cone that's in blue. Well, I can see the radius of that larger cone, and that radius is 8. So this is 1/3 of pi times 8 squared, and we need to know the height of this cone in order to calculate it. So starting at the origin, I need to know how tall this thing is. Well, it definitely doesn't directly tell us the height. What we're going to do is use this little slope right here that we do know to help us. Well, we know that for each 1 unit we go back, it has risen 2 units. So back 1, up 2, back 1, up 2, back 1, up 2, oh, back 1, up 2. My highlighter doesn't like that. So what it's helpful to think about is that we are going back 8 units to get to the center of that cone. And if for each unit we go back, we need to go up 2 units, that puts our height right here at 16. So if we calculate that, we get 1072.3 cubic units. So we're going to do the same thing with the small cone, and it is shown in the red. Same formula, it's still a cone, different radius, different height. Wow, 1/3. Okay, so in this smaller cone up here, its radius is the top of that shape we started with. So it has a radius of 7. And there's a couple ways you could think about the height. You could think about it the same way that for each that we did before, you could think about it that for each unit back, we need to go up 2 units, in which case the height of that smaller cone is 14. Or you could think about that it's the same cone, it's just that the thickness right here of our slice is 2. So if the larger cone had a height of 16, it makes sense that that smaller cone would have a height of 14. So if we calculate this, we get 718.4. So the entire volume of just this frustum shape at the bottom, like a Reese's peanut butter cup or a pie tin, is going to be that 1072.3, subtract away that cone on top, 718. So when we add that or subtract those two, we find that the volume of the frustum is 353.9. So that's it for this lesson. It's all about using revolution and the idea of revolution to find some volumes of different shapes. Let your teacher know if you're having problems with that. And this is the last unit, or the last lesson in Unit 10, so that means we'll be reviewing and getting ready for a test. Thank you.